Hello everyone. Today I want to talk about my choose option is a matrix tree theorem. So I choose this because I'm the a past mathematics major, and I want to use some of the different mathematics to solve the real world problems. And matrix, I think is very important to the linear algebra because it can provide the clear and direct way to represent the cell system or equation. And I choose this topic because I want to know the relationship between the different matrices and how they can be used to solve mathematics problems. So for this theorem, I think this relationship is very interesting and is very fresh to me and also is fresh to you. Yeah, you know that. So uh, for the background, I think that I just have know the basic knowledge about the matrix before I have learned the math 28 and math 22b, and they give me the fundamental structure about this. And right now, I want to talk about some of the basic definition before I choose this topic. First is the non-space. Non-space is a matrix, the size of the all vectors x such as ax equals 0. It is a subset of the domain in the corresponding linear transformation. And intervalis is a scalar. Lambda is of the matrix if there is a non-zero vector such as a lambda equals lambda v. And we want to go to this topic. I have learned the different matrices in this topic. First is the adjacent matrix. Adjacent matrix is a squared matrix used to represent a graph, and the elements of this matrix indicate that whether pairs of the verticals are adjacent or not within the graph. For example, there is a graph. There are four nodes. Is a this is A, there's B, and there's C, and there's D. This is a graph G, and there is the matrix A. This is called the adjacent matrix, and we take the columns of the A, B, C, D, and the row is and the column and the row is A, B, C, D, and the column is also is the same. The full row is A, B, C, D, and for this part for row A and the column A is equal 0 because A is not adjacent to itself. And another example for the row A and columns B equals 1 because A is adjacent to the B in the graph G, because you can see that there's A, there's B, they have the line between each others, so there is 1. And I want to say that the adjacent matrix is also the system matrix because when we transport this, they can the same the row and the columns before the transport this. And I want to I forgot this one. This is basic knowledge about this adjacent matrix because A I G equals 1 if only if the ij belongs to the edge of the G, and aij equals 0 is otherwise. So that is means that for row A column A equals 0 and for row A column B equal 1. And then I want to talk about the degree of the vertex. The degree vertex A is 2 because you can see here is A, and there the two lines belong to the A. There's AB and AC. but there is no AD because there is no lines between the A and D. So the AD is equal 0. Then I want to talk about the degree matrix. This is the second matrix about this option. The degree matrix is a diagonal matrix which contains the information about the degree of each vertex. The Dij equals the degree the verticals I if I equals G, and otherwise is equal 0. This means that this is the transport about the adjacent matrix. You can see that for vertical A, there is two lines equal to the vertical B and the vertical C and the vertical D and the vertical C. They are also have the 2 degrees. So for this point, you can know that. And the next one, this is a special case because there are the self loops. Because you can see that on the one. So in the case of the direct graphs, you can see the on edge that starts and ends in the same node increase the corresponding degree value by 2. And then I will talk about the major project matrix about this option is a Lapplication matrix. Lapplication matrix is equal to the degree matrix minus the adjacent matrix. There is a definition. Given the simple graph G with n verticals VE to Vn, its Lapplication matrix Ln is defined element-wise as Lij equals to the first is the degree the vertical I if I equal G and equal -1 if I not equal to the G and the V vertical I is adjacent to the VG. And third is 0, otherwise it's similar to the before we talked about the 2 matrices, the adjacent matrix and the degree matrix. Here is an example. There is a G, graph G, and 4 verticals is A, B, C, D. And A is a adjacent matrix is called A, and the D is a degree matrix we called D. So Lapplication matrix is equals degree matrix minus A matrix adjacent matrix. So we can know that this matrix is we know that the Lapplication matrix. And then we talk about the spanning trees. A spanning tree is a subgraph of G that includes all of the verticals of G. No cycle is connected. You can see that. We have the 4 verticals is 1, 2, 3, 4. There are the 5 lines belong to each others. But there is not, this is just a graph. It's not a span tree. A span tree is a requirement to the new no cycle and connected. So for you can see that for the 1, 2, 2, 4, 4, 3. This is one of the spanning tree. And another is 3, 1, 4, 2. Just like the N, letter N, letter Z. Then we talk about the cofactors. The cofactor is the number of the is denoted by the Cig and is called the cofactor of L. Right now, the matrix tree theorem is say that the number of the spanning trees of G equals any cofactor of L. You can see that if there's a matrix is a 3 multiplied 3. Big M row 2, column 2, that is row 2, that is column 2, equal to the determinant, that's the exclude this one. So this is a 1, 3, 7, 9. That is basics knowledge about the determinant. And that, after that, we know that matrix tree theorem has one knowledge about the number of the spanning trees of J equals any cofactor of L. And the next one is there's equivalently 1 divided by the n times the product of the non-zero eigenvalues of the L. So we can use this example to illustrate. There are the 3 verticals, is 1, 2, 3. They have the 3 lines that belong to each other. And this is the adjacent matrix, this is the degree matrix, and this is the location matrix. So we know that the location matrix is equal to degree matrix minus the adjacent matrix. So we need to find the eigenvalues of the location matrix. So after that, we know that the spanning trees, the eigenvalues of the location trees is there are the 3 values, but we need to, after we calculate the spanning trees, we need to exclude the non-zero eigenvalue vectors. So this is 3. And after that, I want to talk about why L is always singular. And because singular means that the determinant matrix of a matrix equals 0. And we know that there's an example, and it shows that the determinant of the location matrix equals 0, and the non-space is spanning the 1, 1, 1. So we can know that any of the location matrix is always singular, and they have the non-zero vectors to equal 0. So just like the ax equals 0. Then I use the R to text this as experiment, and I will like I use the road network to the text case. I construct adjacent matrix, degree matrix, and the location matrix, and then I compute the eigenvalues of the location matrix, and I use the matrix tree theorem to calculate the number of the spanning trees. Also, I verify the results by directly counting the spanning trees. These calculations were performed to show how location matrix can describe the structure and the connected of the roadwork. So this example, there are the 6 verticals and A, B, C, D, E, F, and you can see that there are the 7 lines to each others. 1, 2, 3, 4, 7, 6, 1, 2, 3, 4, 5, 6, 7. And there's the adjacent matrix, and there's the degree matrix. You can see here, degree matrix of the vertical A is equal to, vertical B is equal to, vertical 3, C equals 3, vertical D equals 3, vertical E equals 3, and the vertical F equals 1. After that, we can know that location matrix is L equal to degree matrix minus adjacent matrix. So we use the R to compare the eigenvalues of the location matrix, because there are the 6 verticals, and this values is very approximate to the 6 small numbers. So this is the 6 eigenvalues. After that, I use to calculate the spanning trees about maybe it's approximately 11. So this experiment shows that the location matrix can be used to analyze the structure and the relation, the connectivity of the location matrix.